Hi everyone. Today we're going to talk about what a telescoping series is. But before we get to that, let's take a look at this opener question, which is called the Futurama problem because this series was featured on the cartoon television show Futurama, which some of you might be familiar with. Very funny show, a lot of math and science PhDs on their writing staff. So a lot of good math and sciencey humor on that show. So highly recommended. Okay, let's go back to the notes and let's talk about how we would evaluate this. Well, taking a look at this, we have this constant m sub 0. So first thing we're going to do is just bring that out. And then we have 2 to the n on top and 2 to the n on the bottom. And both of those things will cancel out. And that will give us the series from 0 to infinity of 1 over n plus 1. And now, if you start plugging in 0, 1, 2, 3, etc., take a look at those terms, you're going to get the numbers 1 plus a half plus a third plus a fourth, etc., etc. And you might recognize this series. We talked about this last chapter. You might recognize it better if it's written in a different form. Looking at this as 1 to infinity of 1 over n, and again, this is just our constant that we brought out in front, this is called the harmonic series. And this is kind of an interesting series. It has its applications, which we're not going to get into today, but it is also famously divergent, okay? And even if you don't know how to prove it, it's just a famous divergent series, but lucky for us, we can prove that it diverges very easily by the p-test, okay? Okay, so that one's not too bad. Let's take a look at our notes for today. So example 1 says to evaluate. So notice we have another question here that says to evaluate. So typically, not a guarantee, of course, but typically when a question says to evaluate, pretty good chance it's going to converge, right? Again, not a guarantee, but just something nice to think about, right? If you're writing a multiple choice question, right? If I ask you, does it converge or diverge? There's only 2 options in that, right? If I ask you to evaluate, I could give you 4 options of numbers, and then 1 option that says diverge, which is something that you would definitely see on a multiple choice part of the AP test, okay? But for free response, if I'm asking you to evaluate something, it's probably going to converge to a number, okay? So what is this going to converge to? Well, I don't, recognize this as a common series or something that particularly stands out. You can go through the list of techniques we've talked about in the previous notes. You can do ratio tests, right? You can check, is this geometric? You can try to do some type of direct comparison. Nth term test, this one is good on, so that would be a nice quick way to show it diverges, okay? So one thing I'm going to do here, let's just write out some of the terms. Let's just kind of see what's going on here, right? So when n is 1, we would get 2 over 2. When n is 2, we get 2 squared plus 2, so we get 4 plus 2, which is 6. On the bottom, n is 3, and we could simplify this, right, if we wanted to, right? This is 1, this is a third, this is a sixth, right? And this would be a tenth, okay? So we can try to simplify this if we want, but this is going to be an example of a telescoping series. And so what we mean by that, first off, is we have to take this and rewrite this fraction using our old friend, the partial fraction decomposition, okay? So if we take our given fraction, let's go ahead and factor the denominator. And so we get n times n plus 1. And so now we are looking for the a and b values, right? A over n plus b over n plus 1. And so now we're just going to, multiply through by the common denominator, which would be n times n plus 1. Let's go ahead and do that. And so we would get 2 equals a times n plus 1 plus b times n. And now we're just plugging in n values to solve for a and b. And so plug in n equals 0. And so that means that b times n is going to go away. And that gives us that a is 2. And then let n equal negative 1. And that means that this a term is going to go away. And so we can solve for b, and we get negative 2. So our original series in sigma notation, right? 2 over n squared plus n. we're going to start off now by rewriting that as sigma of the quantity 2 over n minus 2 over n plus 1. And so if I look at this, right, now let's try what we were doing in the beginning again. Let's plug in different values for n and see what we get. So if I plug in 1, I get 2 over 1 minus 2 over 2. Now you can see I have this canceled out. We'll get to that in a second. So this is when n equals 1. And now let's do the same thing when n equals 2. I get a plus 2 over 2. So you can see why this one was canceled out. Minus 2 over 3. And we'll see what this cancels out with. Let's plug in n over 3, right? Or excuse me, n equals 3, pardon me. And so we would get a positive 2/3 minus 2/4. Then the next term, when n equals 4, we would get a plus 2/4, which is where that one would cancel out, etc., 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 right? And so this is the idea of the telescope, right? The more it opens up, right, the more we can see. And that's what we have here, right? The more terms of this we write, the pattern becomes evident that every second term, right, is going to cancel out, right? Negative 2 over 2 plus 2 over 2. Negative 2/3 plus 2/3. Negative 2/4 plus 2/4, etc., which means that eventually everything will cancel out except 2 over 1. And that is just 2. Okay? Okay. So a nice little proof here, right, for what this evaluates to. So partial fraction decomposition is our key for this, okay? And then the other thing, and you're going to get good at this, is, you kind of have to write out a few terms to kind of figure out what the pattern is. It may not be as immediate as, oh, the very next term makes it cancel out. That would be great if it was always like that. It's not going to always be, okay? Let's take a look at another one. Example 2 says, evaluate 1 over n squared plus 4n plus 3. So again, when you're looking at, does this converge, does this diverge, right? Again, with this kind of question, you're typically not just going to get asked, does it converge or diverge, right? If you can show it diverges quickly, that's great. That's usually not going to be the case for something like this. So, try to pay attention to the type of fraction, right? If I can do a direct comparison and show that it diverges, that's great. If I can show that it converges, that's not really helpful when the question says to evaluate, right? Because again, think about a multiple choice. You're going to get 4 different numerical options for what it evaluates to. Knowing that it converges doesn't help you out picking one of the 4, okay? So we're going to do, again, partial fraction decomposition on our denominator, and this is the same thing as it was when evaluating an integral. You got to make sure you factor correct. Don't make a silly mistake, right? This is n plus 3 times n plus 1 for the denominator, and so we can go ahead and rewrite this as a over n plus 3 plus b over n plus 1. Go ahead and multiply by common denominator, and so we get 1 equals a times n plus 1 plus b times n plus 3. And now we know what to plug in, -1 and -3. Let's go ahead and plug in -1. The a term will cancel out there. And so we will get 2 times b equals 1. And so b will equal 1/2. And then n equals -3 will make the b term go away. Plug -3 in there. So a is -2, which means a is -1/2. Which means now we can go ahead and rewrite our original series as -1/2 over n plus 3. And, feel free to not write this as a complex fraction, right? Ultimately, it doesn't really matter how I write this because, your question is not going to be, hey, rewrite this series using a partial fraction decomposition and make it look nice. That's not what the question is, right? Now we know what we're going to do. Right, we know we're going to plug in values. But one thing I will do on this, just to make my work a little bit easier, is they both do have a 1/2. I will factor that out. And then, I'm an interesting guy. I like things in a certain order. And so I want the positive term first. So I rewrote it with the positive term first there. And then also, just to not take off any half points on myself, I will put this whole thing in brackets. Okay. All right, and so let's go ahead and start plugging in values. So again, I have the 1/2 factored out right here. Let's go ahead and plug in n equals 1, and so I get 1/2 minus 1/4. Let's plug in n equals 2. I get 1/3 minus 1/5, and so far you're looking at this and you're like, all right, there's 4 unique terms here. None of these canceled out. Uh-oh, did I screw up? No, remember the telescope. You got to keep extending, okay? And let's look for a pattern. N equals 3, ding, ding, ding. I have the 1/4 that is canceling out with this negative 1/4. That's good. N equals 4. I have 1/5 canceling out with this negative 1/5, right? And then I'll keep going, right? If n is equal to 5, I'll get 1/6, which will cancel out with this 1/6, and then I have negative 1/8, and so when n equals 6, I'll get a plus 1/7, which this term will cancel out with. When n equals 7, I'll get a plus 1/8, which this term will cancel out with, okay, etc., etc. And so what's the only thing that did not cancel out, right? Again, I have that 1/2 factored out in front, but the only things that did not get canceled out were this initial 1/2 and this initial 1/3. Everything else will have something that eventually cancels it out. Okay, so this is a half of a half plus a third. Half plus a third is 5/6. Half of that is 5/12. Okay. So overall, right, in the scheme of, doing all of these different types of tests this chapter, these telescoping series questions are pretty nice. Okay, and that's all we have for today. So I will see you next time.